What I'm going to do now is calculate the force on an electron not due to a single charge and not due to a few individual charges, but due to a continuous charge distribution. And this is going to be a little bit more of a challenge. You can't just calculate some point on here and say that that's where, like, pick the middle of the cylinder and just figure out what the total charge is, because it's a varying distances away from it. This part is going to have a much larger effect than the far end of it will. And so we have to deal with this in a different way. We have to use calculus actually and integrate. But here's the situation. This cylinder here has a uniform charge distribution on it of 6.0 times 10 to the minus 15th coulombs per centimeter. And the way that this is usually denoted, when it's a linear charge distribution, you use the Greek letter lambda that you probably used for wavelength last quarter, but that will be the plus 6.0 times 10 to the minus 15th coulombs per centimeter. I'm going to deal with just symbols until I get all the way to the end, and then I'll have to do some unit conversion because I don't want centimeters in my final result. But we'll see how that happens to go. Let's see. So that's what lambda is. I'm going to denote a couple of other things here. I will let L be the length of the cylinder itself, and I'm going to let A equal the distance from all the way down here to all the way up here. I'm also going to just let the x-axis point in that direction. So down here I'll just have that be the origin of the x-axis and let A be that total length. And the reason I'm going to do that is because it's going to show up in my expression here. All right, well, now I'm going to just pick a little tiny length of this thing that I'm going to call dx. And when we actually set this up, we'll think of this in the limit as dx goes towards 0, which is your calculus thing. And where x is going to be is at a distance x away from the origin. Then, how far is that little chunk x from the electron? Well, this is A, this is x, this will be A minus x. And so right here we'll have A minus x. Away from the electron. Okay, and these are all distances I want to know because I'm going to write Coulomb's law down now just for that little chunk of charge and see what little element of force it produces. And I'm going to start by writing a vector expression, and we'll manage to evaluate a scalar expression because it's going to have a common term there. But the little chunk of force that this little piece of charge contributes is going to be, well, we'll have K sub E, and then we'll have the charge of this thing. Oh, what's that going to be? Well, it's going to be lambda dx. Okay, that has a length dx. This cylinder has a charge per unit length of lambda, and that amount of charge will be lambda dx. That's one of the conceptual hurdles that you need to jump over in doing a new problem like this. So K sub E, lambda dx, this is like our Q1. Our Q2 is going to be the charge of the electron, which is E, and in this case it's going to be negative 1.602 times 10 to the minus 19th coulombs. The electron is going to be pulled toward this cylinder. Okay, and let's see. That's my numerator. K sub E, Q1, Q2, and then the distance between that charge and the electron is A minus X, and of course that has to be squared. And the direction, this is a vector after all, it's going to be in the I hat direction, but the fact that this is negative is going to turn that around and pull it in that direction. But that won't happen until the end, when I actually plug in the numbers. So let's see what the integral is going to look like. The integral, f, will equal adding up all of these little df's, and that's what an integration is doing. Now it's very hard to picture this as the area under a curve, and so I'm not even going to try. I'm just going to add that thing up. And let's see, I'm going to pull everything outside the integral that doesn't change throughout it. K sub E doesn't change, lambda doesn't change, E doesn't change, and I hat doesn't change. So K sub E, lambda, E, I hat is outside the integral. Inside is dx divided by a minus x quantity squared. And the limits of integration, I have to consider charge from down here where x is 0 to up here where x is equal to L. And that's what I have. All right, well, I'm going to do a substitution on this thing. I can't remember what this particular integral happens to be. Maybe some of you can, because you might have just had second quarter calculus last quarter when you do all the integrals, but I will let alpha, let's see, equal a minus x, and d alpha will equal minus dx, or dx is equal to minus d alpha. Also, something else I have to consider is when x equals 0, alpha is going to equal a. When x is equal to L, alpha will equal a minus L. And so that's everything I need to do to rewrite this thing. And now I'm just going to concentrate on the integral. I remember I've got this stuff out front of it. So my dx over a minus x squared is going to transform into minus, I've got a minus dx, or minus in front of the d alpha, so I'll just put it in front of the integral. And d alpha over alpha squared, and I know how to do that integral, but the limits of integration are a, that's what is replacing the 0, and a minus L will replace the L. So, and that's it. That's all I have to do. Well, that integral, d alpha over alpha squared, is minus 1 over alpha. And so I'll have a minus 1 over alpha evaluated at a and a minus L. Sorry, this is kind of bunched together. And the minus multiply to a plus, so 1 over alpha evaluated at a and a minus L. And that's just going to be 1 over a minus L minus 1 over a. Okay, now you could just evaluate this number-wise at this point. You'd have units of centimeters to the minus 1, I think. But, well, what I'm going to do is get a common denominator for these things. I still have the tendency to avoid doing anything with a calculator as long as possible when I solve a problem. And so common denominator is going to be a times a minus L. And if you multiply top and bottom of the first one by a, top and bottom of the second by a minus L, you will get the a over a times a minus L minus a minus L over a times a minus L. I taught algebra here in addition to my physics classes. I taught those for a long time, and I wished I'd taught a few years of algebra before I took calculus. It would have made that so much simpler. Anyway, my numerator becomes a minus L, and my denominator is a times a minus L, which there's nothing left on top except an L, nothing left on the bottom except a times a minus L. And if I actually stick in the numbers now, L was equal to 15 centimeters. And a times a minus L is going to be 20.00 centimeters. A minus L is 5.00 centimeters. Look at that. I want another piece of paper. Let's see. That integral, minus the stuff that's multiplying it out in front, turns into 15 over 5 centimeters, ends up being 3.00, and so I end up with 3.00 centimeters. No, not centimeters anymore, those have divided out, over 20.00 centimeters. So I've still got centimeters to the minus 1 on the bottom. Okay, let's go back to our force expression, which just has these things in front of it. And so the force that's exerted on the electron now is just going to equal K sub e lambda E I hat times 3.00 over 20.00 centimeters. Time to plug in the numbers. And I'm going to remove this I hat out to the end here. So the force on the electron will be K sub e, which is 8.99 times 10 to the 9th Newton meters squared per coulomb squared, times lambda, which is plus 6.0 times 10 to the minus 15th coulombs per centimeter. So that takes care of one of the coulombs there, times the charge on the electron, which is minus 1.60 times 10 to the minus 19th coulombs. So now I've got coulombs squared on top. That takes care of those, but I've got Newton meters squared per centimeter. And then almost bringing up the rear here is my 3.00 over 20.00 centimeters that are on the bottom. And then I've got an I hat there. Okay. I think I'm just going to multiply these out and keep track of the units. What I'll have for units are Newton meters squared over centimeters squared when I multiply all this stuff together. And I'm just being really careful not to monkey with that, and a minus sign on it. So see what we get. Whoops, not times. Okay, so far I have, let's see, I can only keep two significant figures at the end. So I've got 1.3 times 10 to the minus 24th, and this will be Newton meters squared per centimeter squared. Those are the units that are left. In the I hat, a minus sign in front of that, and an I hat on this. Well, I happen to know that 100 centimeters divided by 1 meter is equal to 1, and if I just square that, then I'll have centimeters squared on top, meters squared on the bottom, which will divide with those things. And this is 100 is 10 squared, this is 10 to the 4th, so I'll be multiplying by 10 to the 4th. Let's see, I wonder if I missed something. That's 6. Seems to work out. I'd done this calculation to check myself. Oh, yeah, I'm fine. It is minus 1.3. So it ends up being minus 1.3 times 10 to the minus 20th newtons in the I hat direction is the force that is on that electron. Okay, so there we did it. And notice I worked all the way through this problem, did a lot of work before I touched my calculator. And that's typical for a lot of problems. You have to do a fair amount of setup work on the things. Now, part B of asks, what's the acceleration of the electron? And something to be careful of here, it's the acceleration of the electron the instant that it is at this point. It's accelerating in this direction because that's the direction of the force on it. But as soon as it gets closer to this cylinder, the acceleration is going to become greater, and it'll become continually greater until it smacks into the end of that cylinder. So, and then we're not going to worry about it anymore. But we're just interested at this instant. What's the acceleration? So, what will that be? Part B, the acceleration of the electron is just going to be the force acting on it divided by its mass. And so we'll just take the minus 1.3 times 10 to the minus 20th newtons in the I hat direction, divide by the mass of the electron, 9.11 times 10 to the minus 31 kilograms. Okay. Some of these numbers, you're going to be looking them up a bunch of times, and you might just take some kind of a note card and write down K sub E, mass of the electron, charge of the electron, mass of the proton, and so forth, and get those things. So when I do that, I end up with, to two significant figures, minus 1.4 times 10 to the 10th meters per second squared in the I hat direction. So that's the acceleration of the electron in vector form. I probably would have been content with just getting the magnitude of the electron, or the acceleration, and knowing which direction it's going. So there's a pretty complex problem, and integrating to find something for the first time this quarter at least.